Welcome to the fourth installment of the Probability and Statistics Math 3350 online course. Today we're going to be talking about conditional probability, and this is going to be really important to help develop the idea of when two probabilities are independent of each other. So with conditional probability, we have this idea about the probability of A occurring. So normally the probability of A, P of A, is the probability that event A occurs. But for conditional probability, we're trying to calculate the probability that A occurs given that we know event B has already occurred. All right, so this is read as the probability of A, and then the vertical bar means given that this event has already occurred. So the formula is the probability of A intersect B divided by the probability of B. So we'll look at this visually in just a second. This formula is fairly easy to work with, but the more important thing is the definition of independence, right? So we are going to call two event sets A and B, we're going to call them independent, provided that the probability of A is equal to the probability of A given B. In other words, even if B has already happened, right? So B has already happened here, the probability of A is still equal to the same thing, right? The fact that B has happened already doesn't change the probability of A. And the same for B. It turns out that these are equivalent ideas, and that's shown in the notes. You should definitely read the course notes each time, and so that proof is given. But it does make sense, right, that if the probability of A doesn't change whether or not B has happened, then the probability of B occurring shouldn't change if A has already happened. So both of these are true at the same time. And this is definitely important. We love independent event sets in probability because we can work with them completely separately, calculate the probabilities in both of the simpler subsets, and then either add or multiply as is appropriate. So we love being able to separate these sets into independent probability experiments. Okay, so let's do an example. So suppose we have two cards drawn at random from a standard deck of cards, and we're going to let R2 be the probability that the event set that we draw a red card second, and B1 is going to be drawing a black card first. And so they ask us to find the probability that a red card is drawn given that the black card was already drawn. So when you do conditional probability, some of the simpler ones, like are part of this course, some of the easiest ones, you just can restrict the probability space, right? So that's what we're going to look at first. If I restrict the probability space by assuming that a black card has already been drawn, what do I know about the deck? Well, the deck had 52 cards in it, right? But if a black card has already been drawn, that means one of the 52 cards is already gone, right? So my probability space, if I restrict it to what happens after the first card has been drawn, there's only 51 things, right? And how many red cards are left? Well, there were 26 of each, red and black. Now there's still 26 red, and there's only 25 black because one of the black cards was drawn. So this is the probability approach when I restrict the probability space. Just assume the first event has happened, the event R2 has happened, and calculate B1. So that's how we're getting the probability that we draw a red second, given that a black has been drawn first. We can also use the formulas, right? So the probability formula says that the probability of B1 given R2 is equal to the probability of the intersection divided by the probability of R2 is actually what we have. Right, so the difficult thing is calculating the probability of this intersection. I'm sorry, I said the thing that's given, we're doing this, right? Calculate the probability that red is drawn second, given that black is drawn first. Well, the hard part is calculating this probability. What is the probability that they both happen? Well, if they both happen, then this is the first 26 over 52 where I draw the red card. And then inside parentheses is the 26 over 51 where I draw, I'm sorry, the first one was where we drew the black card first. And the second one is where we draw the red one second. Okay, so when I put this probability in the numerator, right, that's here, divided by this probability, right, that's just applying the formula, and I do a little simplification, and I do come out with the same exact answer as we had up here. So the formulas work, but sometimes, in this case, it certainly was easier to just restrict the probability space. The second example we want to take a look at is the conditional probability that we draw a prime number given that we know the number is even. Well, the first approach is to restrict the probability space. If we restrict the probability space, we say, look, let's just restrict ourselves to the numbers that we know are even. And then once we've just restricted ourselves to the even numbers, let's calculate what the probability is of drawing a prime. Well, one of the 5 even numbers is prime, so the probability is 1/5. The second approach is to use the formula, which is just as straightforward. It may look a little awkward, but this is when you need to write out the formula, right? So this is important, this pattern. The probability that the event prime happens, given that the event even has already occurred, is prime intersect even, and notice that the event that's second, right? Notice I'm kind of underlying the even. So that's the pattern we need to remember with this. And we can calculate those. Those are pretty straightforward. Prime intersect even. Well, the only thing that's in the intersection of prime and even is 2. So the probability of this intersection happening is 1/10. And what's the probability of even? The probability of even is 1/2. So I take 1/10 and divide by 1/2, and I get 1/5, just like I did using the other approach. And I also want to talk about the Monty Hall problem. It's a classic. It's iconic in math circles. It's a great example of conditional probability. It's a little bit counterintuitive. Smart people have disagreed vehemently on the right answer, and so it's a good one. And I also want to tell you about the YouTube channel Numberphile. Definitely a great YouTube channel. It's some cool math professors who get together and they make these videos, not for math geeks, they make them for the general population. So they're really good to help explain things to little kids like in elementary school, and they do these nice high production videos. So check out Numberphile and the Monty Hall problem. Those links are available in D2L. Example 3 refers back to a deck of cards, and in an earlier video we used F for face cards, B for black cards, and E for even. And so we're supposed to determine whether the following probabilities are independent. So the probability of a face card and the probability of black, the probability of a face card and the probability of even, and the probability of even and a face card. So on the tablet, I went ahead and wrote out what we're looking for. Let's look at these probabilities. The probability of black, that is 1/2. Half the cards are black. Actually, let me switch, and I'll say that 26 of 52 cards in the deck are black. And how many are face cards? Well, there are 12 face cards. There's the Jack, Queen, and King, and 4 of each of those. So 12 over 52 is the probability of drawing a face card. The probability of drawing an even, now 6 of the 13 values were even, the 2, 4, 6, 8, 10, and the Queen. So this is 6/13 or 24 over 52. So the probability of drawing an even card is not 1/2. That's kind of the important thing I wanted to note. Okay, so let's look at the number of outcomes in the black intersect even. Well, half of these over here, half of these 24 outcomes are black, half are red. So black intersect even is going to be 12 over 52. Right? Face cards, well, of these 12 face cards, half of them are black, so the probability of black intersect face cards is 6 over 52. And then even face cards. Okay, well, those are just the queens. And therefore, we have 4 over 52. And I'm going to leave the denominators of 52 because with this formula, that's just going to make sense. I'm not going to reduce. So let's check on the probability. We're going to see if B and F are independent. So we'll look at the probability of B given F. What is the probability of drawing a black card given that we know a face card has already been drawn? So the conditional probability formula tells us that B given F is equal to the probability of B intersect F divided by the probability of F. Okay, well, we have those values here, right? We have the numerator value is 6 over 52, and the denominator value is 12 over 52. So I have 6 over 52 times 52 over 12, but the 52s cancel, and 6 over 12 equals 1/2. Well, notice that the probability of B given F is 1/2, but the probability of B is also equal to 1/2. So the probability of B doesn't change whether I've drawn a face card first or not. Half of the face cards are black, so I can draw it first and then I have a probability of 1/2. Or I can not bother drawing anything at all and I have a 50-50 chance of drawing something that's black. So now let's look at the probability of drawing a black given that we know we've drawn one that's even. So probability of B given E. And again, it's the probability of the intersection of B and E over the probability of E. And we can read these off. The probability that it's even is 24 over 52. over 52 divided by the probability of even. Sorry, I messed this up. The 24 over 52 was supposed to go in the denominator, and the 12 over 52 was supposed to be in the numerator. Okay. So once again, I think you can see that we end up with 1/2, but these sets are not independent. Why? I'm sorry, these sets are independent because the probability of drawing a black is the same whether I've drawn an even card first. Half of the even cards are black. All right, so finally, let's take a look at the probability of E given F, or F given E. Okay, I'm not going to write down the formula again. I'm going to go get the intersection of F and E, which is 4 over 52. I'm going to divide that by the probability of E, which is 24 over 52. And now the 52s will cancel, so I end up with 4 over 24, or 1/6. Now I end up with sets that are not independent, right? So this is 1/6. The probability of F is 12 over 52, which is 3/13. And 3/13 is not equal to 1/6. So we know that F and E are not independent events. For our final example, I'm going to ask you to play around with an interactive app called a geoboard, and the link is in D2L. It's also in this handout. If you're looking at it in digital form, you can just tap on it. So we are going to be looking at this geoboard. It looks like this. So we have a 16 square grid, right? A 4x4 grid. So there are 16 squares. And that's our probability space. And we're going to create an event set A. We're going to use these bands. Sorry, we're going to use these bands to create event sets. and I'm sorry, I'll have to do that once I get over to the iPad. You use these bands and you can create event sets. And then we're going to calculate those conditional probabilities. And we're going to see if we can find event sets A and B that are independent. And just to introduce a topic, we'll talk about this in the very last probability topic that we have, but we have these infinite probability spaces, right? These are areas now, so there's infinitely many points in them. So when we have these infinite probability spaces, what we do is, instead of counting cardinality, right, because infinity over infinity is an indeterminate form. So what we're going to do is we're going to calculate the area of S, and we're going to calculate the area of the total probability space, which for our geoboard will be 16 squares, right? 16 units squared. And the ratio of the areas is what we'll consider to be the probability of A. Okay, so here is the geoboard. And sorry, I'm trying to get this app so you can see it here. All right, and so we can take these rubber bands, they're simulated rubber bands, and we can create event sets like this. So this red band event set is 1/4, right? There are 1, 2, 3, 4 of these areas, and so out of 16 total, so the probability of drawing a red is 1/4. Okay, well then I can grab a blue rubber band, let's say, and put it like this. Okay, now with the blue rubber band here, let's fill them in so you can see. So the blue rubber band is half the area, right? The blue rubber band has area 1, 2, 3, 4, 5, 6, 7, and 8. Those areas, 1, 2, 3, 4, 5, 6, 7, 8, 8 out of 16. So the probability of blue is 1/2, and the probability of red is 1/4. So the question is the probability of blue given red the same thing as the probability of blue? Let's see if I have room over here to do the probability of blue given red. Okay, well, if red has already happened, we're just worried about these 4 squares. And if I know that one of these 4 squares has already been chosen, what's the probability of choosing a blue one? Well, half of them, right? Square number 3 and square number 5 are the only two. So this is equal to 1/2. And the probability of blue is equal to 1/2. All right. So the answer is yes. The way these are drawn, the probability of blue given R is 1/2. The probability of blue is 1/2. So the events drawing a blue dot, if you pick a dot at random here, drawing a blue dot, given that you've already drawn a red one, is the same as the probability of just picking a blue one. And so let's just change one of the event sets. So what if I do this? Well, now it's still the same thing, right? I have a slightly different look here. Right now, I am dealing with just this 2x1 rectangular grid. And the probability of drawing red is different, but notice the probability of drawing blue, given that I'm drawing red, is still 1/2, right? There's 1 blue square out of 2. So when I leave them like this, they are still independent. So if I made the red bigger, right? Still, half of the possible squares that I could pick, if I've already picked a red one, will also be in the blue Okay, so let's get one that is not the same. So what if I do this? Well, now look at what's happened. Okay, so if we move these over to the right, now I have 6 red squares, but 4 of them are blue. So the probability of blue given red has been drawn is 2/3, right? 1, 1, 2, 3, 4 out of the 6 total, right? So now the probability of red is different than the probability of red given, excuse me, the probability of blue, which is still 1/2, is different than the probability of blue given red, which is 2/3. So you can play around with that, but it is helpful to see if you can find a couple different pairs, a couple different configurations of sets that are actually independent, and see what that looks like visually on the geoboard. So that's a wrap for today. Make sure that you read the course packet and do those problems there. And after that, you should definitely be ready for the completion quiz. Good luck.